Hi, Tony.
Hey,
Right, let me share my screen. Right, so today we will be talking about chapter 16.4, which is related to the absolute motion analysis. It's not like it's not a new concept, just like just some application. What we have been talking about in terms of the relationship between the angular velocity and angular acceleration. So, based on what we talked over the last couple lectures, omega is equal to d theta dt is the time rate of change of the angular position, and alpha is the time rate of change of the angular velocity. So here we need to apply this in a more complicated problem. So let's have an example. So let's illustrate the relationship between two bodies. One of them has a linear and also an angular motion, and the other one has an angular motion. So for this example, it says that we have a large window. This window has a length of 2 meters and open using a hydraulic cylinder AB. So this hydraulic cylinder is extending in its length, so this window can open. So it says if the cylinder extends at a constant rate of 0.5 meter per second, determine the angular velocity and the angular acceleration of the window at the instant where theta is equal to 30 degree. So at some point when this window is closed, the arm AB was at this point, so B was here, and when the arm is getting extended with this constant rate of 0.5 meter per second and put a line under constant, that means it doesn't have an acceleration. So when the arm extends, the window open, and the window makes an angle theta with the vertical. So right now we need to relate the motion of the arm AB to the motion of the window. So if you think about it, you can like get this triangle at any instant theta. So let's assume that we have this triangle and we have our arm, our hydraulic arm, something like that, at any instant. So we know for sure that this distance is 1 meter and it will not change, this 1 meter. But this distance will change, so we will put it variable s, and this distance will not change and it will be 2 meter. And this angle will be changing with the changing of s, and this will be theta. So you can make a relationship between s and theta. As s is increases, the theta will increase. So let's make this relationship. So for this relationship, you can do this using Pythagorean theorem. So you could make like a line like this, and this will be 1, so this will be 1 sine theta, and this will be 1 cosine theta, and the other part will be 2 minus cosine theta, and then you can have s square will be equal to sine square theta plus 2 minus cosine theta squared. So this is one way to do it. And also there's another way to do it using the cosine rule. So for the cosine rule, the s squared will be equal to the other two sides square. So it will be 2 square plus 1 square minus 2 multiplied by the two sides, 1, 2, multiplied by cosine the angle between the other two sides, cosine theta. So this is how you can do it using the cosine rule or using the Pythagorean theorem, and should give you the same answer. Like after you expand this term, it should give you similar like this. And you will find the cosine rule and the sine rule in the dynamics sheet all the way over the top of the sheet. So you can use them. And when you have like s squared, it will be s squared will be equal to 2 squared 4 plus 1 minus 2 multiplied by 2, it will be 4 cosine theta. So this will be 5 minus 4 cosine theta. So right now we were able to get a relationship between s and theta. So s squared will be equal to 5 minus 4 cosine theta. And if we want to like get some values, like what is the value of s at theta equal to 0, like when this window is closed, so it will be, let's put theta first. So at theta equals 0, so s squared will be equal to 5 minus 4 cosine 0, which will be equal to 1. So it will be 5 minus 4, so this will be 1 meter. So actually, yes, when we are here, the s will be equal to 1 meter. And because we are talking about this as the length of this arm, so the arm will be coming back to this point, and at theta equal 30 degree, which is the one given here, it will be equal s squared. And actually s squared equal to 1, so s will be equal to 1 meter. And here s squared will be 5 minus 4 cosine 30. And this should give you something, and finally you will have s will be equal to a 1.239 meter. So we got s at 30 degree. So this is not what is required. What is required is the angular velocity and the angular acceleration. And actually we can get this from this equation. What if we have right now s squared is equal to 5 minus 4 cosine theta? What if we differentiate this with respect to with respect to t, sorry. So we can get velocities. So if we differentiate s with respect to t, it will give us 2s multiplied by ds dt. Why? Because if we differentiate this item or this term with respect to s, it will give 2s only. But we are differentiating with respect to t, so we will have ds dt at the end here. And let's continue the differentiation of 5 with respect to time. It will be 0 minus 4. And let's differentiate cosine theta. It will be negative sign. So this will be 4 sine theta. And we will have d theta dt outside. We know the ds dt is the vs, and which is given here in the problem, like the time rate of change of the s. So we will have 2s multiplied by vs will be equal to 4 sine theta, and d theta dt is the omega. And that's what is required, the first requirement in this problem. So at theta equals 30 degree, this equation will be like 2 multiplied by s at 30 degree, which is calculated here, 1.239. And vs is constant. The vs has a constant rate, 0.5 meter per second when theta is equal to 30, so we will have 0.5, and this should be equal to 4 sine 30 multiplied by omega. So we can get omega from this equation, and this should be equal to 0.6195 radian per second. So we got the first requirement. So the second requirement, we need to differentiate the equation that we got here one more time with respect to t. So let's do it. It's a little bit harder, but we can do it, dt. So if we differentiate 2s one more time, it will give us 2 ds dt. And we have another ds dt outside, so this will be squared, and then we will differentiate the second term with respect to s. So we will have the first term 2s multiplied by the second derivative ds dt. So it's the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first. And this should give us 4 sine theta. It will be 4 cosine theta, and we will have the theta dt outside, and we have another one, so this one will be squared plus 4 sine theta multiplied by the derivative of d theta dt, and this will be given the second derivative d theta dt. So the derivative of the first term multiplied by the second term, and then plus the derivative of the second term multiplied by the first term. So let's see what we have here. We have the second derivative of s, which means the acceleration of the arm, and it's equal to 0. Why? Because here it says it extends with constant rate. That means the acceleration of the arm is 0. So we have this as a 0. And what else we have? So let's put numbers. So we'll have 2 multiplied vs square, which is 0.5. Plus 2 multiplied by s at theta equals 30 degrees. So it will be 1.2939. And this should be equal to 4 cosine 30 multiplied by omega square. And we just got omega 0.6195 square plus 4 sine 30. And this should be equal to alpha, because the second derivative of the theta is alpha. So here is the only unknown is alpha, and you can get it, and this will be equal to negative 0.4147 radian per second. So this problem is just like you making relationship between the s and theta, and then you differentiate this relationship with respect to t, so you can get omega, and another one so you can get alpha. So does anybody have any question about this problem? Or any complication, any issues? All right, so just like a direct application to review the relationship between the angular velocity and the angular acceleration. So with this, let's start to chapter 16.5. Relative motion analysis. Right, so for relative motion analysis, we will have, let's assume that this is our xy coordinate. And we did this before, but let's review it again. And we have like our rigid body is something, let's assume this is our rigid body, and this is A, and this is B. And if we are measuring the position, so let's talk first about the position. One position. So for the position, we will have, this is the position of B with respect to O. So this is our B vector. And this is the position of A with respect to O. So we will have our A vector. And this is the position of B with respect to A. And this is RB with respect to A vector. And as we discussed last time, that the position of B on this body will be equal to the position of A plus RB with respect to A. So this is how we formulated last time. If you want to go to B, you can go to A and then move from A to B. And if we are talking about pure translation motion, so the RBA will be equal to 0. No, I mean like velocity, if we are talking about velocity. So this is not a changing if we are talking about translation. Like imagine that we have this pen, just like give me one moment, I will bring 2 pens. We will have an interesting example in a few moments. So let's talk about this bin first. If it's making translation, so this bin, if it's making translation, it will be keep moving, and the relative velocity of B with respect to A is not a changing. It is not a changing in the magnitude. It's the same, and it doesn't changing in the in the direction. So it doesn't make this or like that. So let's write this clear here. The this term cannot change. Right, so this term cannot change in magnitude, but can change in direction. It doesn't change in magnitude and doesn't change in the direction if it's a translation motion. But it can change in the direction if you have a fixed axis rotation. So the RB with respect to A is keep changing its direction. Or it's a general plane motion, like the bin is moving in the space and keep changing in the direction. But we can agree on that this will not change in the length, I mean in the magnitude, because it's a rigid body. If it's changing in magnitude, so it is not rigid body anymore, like if you have a rubber or something that is compressed or have any deformation, so it is not rigid body, and all our rules that we have been learning here will not be applicable. So let's study next is the displacement. And it will be general displacement. Let's have this body out here like this. Let's make it and this body moved like that to be here. So if this is point A and this is point B, and let's assume that this body is making a very small displacement. So the A moves from here to here. I'm just like extending this displacement so we can have better vision. And this is B, and this is how B got here. So we can call this as DRA vector, and we can call this as DRB vector. So let's analyze this motion. So let's assume that we have these two bins, and actually it's one bin, and this bin was at this location and moved to be at this location. Can you guys confirm that you are seeing my hands? It's not outside the extent of the camera?
Yeah.
Okay. So we need to move this bin from this position to get to this position. So what happened? Like this bin was like here and came back to this position. We can analyze this motion at two steps. We can assume that this bin made a translational motion to get to this point and then made a rotational fixed axis rotation to coincide with the other point. Like it was making a translation until it get here and then made a fixed axis rotation to be like this. So if we want to put this here, we can assume that and we can have this as point B, and let's make this. So we will assume that this will be DRA similar. So we will assume that this bin move translation. So we will have DRA and DRA at B, and then this bin make a rotation like this with an omega to get to point B, and we can call this as dRB with respect to A. So it comes here and then comes here. If we want to take this triangle outside, so it's something like that. So this is how P was moving from this point to this point. So we will assume it get to dRA vector and then made another one dRB with respect to A, and this is dRB vector. And actually, if we want to get the value of dRB with respect to A, so it should be equal to but this will be velocity, it should be equal to theta. Like if we can get, so this will be d theta, and we have as well this distance. This is RB with respect to A, so dRBA will be equal to d theta multiplied by RB with respect to A. And actually, we can write a formula here that dRB vector will be equal to dRA vector plus dRB with respect to A. And that's true because if you want to get from this point to this point, you will have to go like this and go like this. We will have to sum them. And this should be equal, if we want to divide this over dt, so this will be another equation, which will be the V at B will be equal to the V at A plus the VBA vector. So what is the VBA vector is equal to? So we can have this from here. Let's have dRBA dt. It will be something d theta dt multiplied by RB with respect to A. So we just differentiate this term, and we know that RB is constant, is not a changing in magnitude. So this will be equal to omega crossed product by, and actually, if we want to have it in the vector term, it will be something like this and something like that. And this is RB with respect to A. And that's true. If we want to get the velocity, we multiply omega by R. So here, if we want to get the VB with respect to A, this part, it should be omega cross the product by RBA. So from here, we can conclude this, that the VB vector will be equal to the VA vector plus the omega crossed by RBA vector. So it's something like this. You have a body and plus two terms, and we have here, let's draw VA, and this is VB vector. So this is a general motion. VA is moving in a direction and has a magnitude and direction different from VB. So we can divide it as a translation. So all this body will be having a translation with VA down and VA here. And then we will have a rotational motion with an omega and with VB with respect to A at this location. And we can get it from RB with respect to A. So this is, if we look at the lower term here, it it will be VB vector will be equal to VA vector plus VB with respect to A vector. And this one is the omega of the body multiplied by RB with respect to A. Does anybody have any questions on how we derived these relative acceleration between A and B? All right, so let's do some applications on how can we get the relative motion between different points on different bodies. So what if we, for example, if we have an arm like this, and this arm is restrained at point, let's name this point A, restrained like this, like you have a hydraulic cylinder at this location. This arm can rotate, can make an angle omega, but cannot move in y direction. It's only allowed to move in the x direction, either this way or this way. And this arm from here is attached to another arm, which is bent from the bottom here. And let's see how does this motion look like. So this point is bent, so we call this an instantaneous center of zero velocity. And actually it is not instantaneous, it's a permanent center of zero velocity. But as it's permanent, it's also can called instantaneous. I mean, like at the instant that we are studying this body, it has zero velocity. So we can call this an instantaneous center of zero velocity. You can call it ICZV or IC instantaneous center. So the velocity here is zero. So if we want to get the velocity of this point, we can get it from two sides. You can get it like, let's name this as B and let's name this as C. You can get this VB with respect to C or VB with respect to A. If we will get VB with respect to C, it will be perpendicular in this direction, like assuming that this body is rotating with omega, and we will call this omega BC, which means it's for the arm BC. So as we learned it from the last time, if we want to get the velocity at the end point, so we multiply the omega cross product by the R BC, and actually the velocity will be perpendicular like this. So this is VB with respect to C, and actually this is equal to VB. So if I put VB here, will be equal to VC plus VB with respect to C. And we know that C has a velocity of zero because it's restrained from motion. So right now, we can prove that VB is equal to VB with respect to C. As you are relating B with the instantaneous center of the zero velocity, so the absolute velocity will be equal to the relative velocity, like you are comparing. So this point is not moving, but this point is the only one is moving. So you are relating a point that moves with a fixed point. So it should be equal to each other. Okay, so this is for the VB. So what if we want to get the VB with respect to A? Right now, A moves, like when this arm moves with this omega, you will have this one will be moving this way. Like, for example, if this body, let's make a circle like this. And if our body come here, it will be something like this. So that means that the other body is moving this way. So if we want to get VB with respect to A, it will be something like, let's make it another color here. It will be something like this. VB with respect to A. Because we have this body have an omega in this direction, and if we multiply the RBA, the omega cross product by RBA, it will be perpendicular to this line, and A is moving, so you should be careful if you are getting So we can say VB will be equal to VA plus VB with respect to A. Right now, VA is not equal to 0, so we have VB with respect to A, and it's perpendicular to this line. So this is how we can get the VB from different one. And be careful in the exam when I ask you about VB or VB with respect to A or VB with respect to C, and you should be able to know the values of each one of these. So most of the problems will be given like omega BC, and from omega BC you can get VB, and once you get VB, you can get the VA and the omega of the other body. Does anybody have any questions? How can we identify the relative and the absolute velocity at B? Okay, let's make this complicated. What if we have a multi-bar linkage, like you have a bar like this, and then you have a bar like, it's not a bar, it's not a line. Okay, let's have this, and that. And before I do this, I want to just like get back to this problem to talk about the, so we got the instantaneous center of zero velocity of the body BC. So what about the instantaneous center of the zero velocity of the body BA? How can we get it? As I taught you last time, if you want to get the instantaneous center of zero velocity, you will have to know the velocity VA and VB in terms of absolute velocities. So let's get these velocities. So I know that if I have omega is moving in this direction and this one is moving in this direction, this body will be moving in this direction. So this is the absolute velocity VA. And I know that this is the absolute velocity VB. So what I do perpendicular to each one of these. So I made a perpendicular line like this, and perpendicular line to this velocity like this, and this is the instantaneous center of the body BA. How? Because this is where, so like the omega is rotating about this body, so here's our omega, and this is our R, so we will have, here's the VB, it's perpendicular to this line, and this one is perpendicular to this line. So this is the instantaneous center of zero velocity of these two bodies. If you extend this line in this way and extend this line in this way, they will not meet, they will not intersect to each other. They only intersect down there. Why? Because this body is rotating this way. Like we have our omega, the first one is moving this way, so the second one will be this way. What if this one is moving in the other direction? So you will have the velocity in the other direction, and this one is going this way, so you will have to extend this up and extend this up, and you will get the instantaneous center, and the omega will be in the opposite direction, like this, if this is moving this way. So this is how we can the instantaneous center of zero velocities of all the bodies in the problem. And the instantaneous center of zero velocity is very important because you can have this equation, because VC is an instantaneous center of zero velocity. That means that the velocity of C is equal to 0, and make the problem very easy. Like you can have VB is equal to VBC. So let's see this on a complicated problem like this one. You have a multi-bar linkage. We have 3 bars connected to each other and bend at this location. And you are given that this is O, A, B, C. And you are given that the arm OA has an omega in this direction, omega OA is moving in this direction. Let's see what is the other omega. So what do you think, guys? How about the arm AB? If we have OA is moving this way, what about the omega of AB? Does anybody know how the AB will be moving? Is it clockwise or counterclockwise?
Wouldn't it be clockwise as well?
Exactly. So what about the arm BC? Is it going to be counterclockwise or clockwise? So if we have OAs moving this way, yeah, go ahead.
Oh, I was going to guess clockwise again.
Okay, let's see what will happen. If we have OA is moving this way, then AB will be moving this way. So this point will go down, right? This point will go down. That means that this bar gets here. That means it's moving this way. So it's counterclockwise. So this will be omega BC. So it will be, this is how I imagine the omegas from the one bar is moving. So let's get velocities. So let's talk about first about the instantaneous center of zero velocities that are very obvious. So from here, at this point is bent, so I know O will not be moving. So this is an instantaneous center at O, and this point will not be moving. So this is instantaneous center at C. So VC and VO is zero, will not ever moving. So what about P and A? Let's see if they are moving or not. Both points are moving. That means that the instantaneous center will be outside the body. And we need to find where is this based on the omegas. So based on the omega that we have here, the VB will be moving this way, VA will be moving this, it will be perpendicular because the omega is in this way, so the VA will be in this way based on the right-hand rule. And knowing that omega BC is in this direction, so the absolute motion of B will be in this direction. So we got the absolute direction of VB and VA. So based on this, I can know where is the instantaneous center of zero velocity. If you want to do this, you will do perpendicular to VB and perpendicular to VA. So this is the instantaneous center for body AB. So this is how get the instantaneous center for the third body. So this is perpendicular, and this one is perpendicular here. So this is the instantaneous center of the body AB. Okay, so let's get relative velocity. If you got VB with respect to C, it will be equal to VB because VC is not moving. But if I get VB with respect to A, it will not be equal to VB. It's different in magnitude and direction because A is moving and I'm measuring B with respect to a moving point. So what do you think about the velocity of B with respect to A? I should draw a perpendicular. Is it going to be in this way or in this way? Is it up or down? Does anybody know? And you are given the omega AB here. We were able to get this. So from
It would
this,
be
yeah,
down from the right-hand rule.
exactly. Because omega AB is moving down. So if we are measuring B with respect to A, so we will look at the omega AB, so it will be going down like this, and this one will be wrong. So what if I want to get VA, so let's write this, VB with respect to A. What if I want to get VA with respect to B? Is it going to, so it should be perpendicular on the line. Is it going to be up or down? Given the omega AB that we have. So you know that omega is moving like this. So VA with respect to B will going up. It's something like that. So this is how omega rotate, is in this direction. So A with respect to B will be going up, something like that. So maybe in tomorrow's quiz, maybe in the other quiz, you will be given a problem. You should be able to determine VB with respect to A, VA with respect to B based on the omegas. So let's solve the same problem and let's change the omegas. I might like Okay, let's have this. And let's put here O, A, B. Let's make B down because we will have a lot of C. And let's say you are given in the problem that the omega of BC is in this direction. So if omega BC is moving in this direction, I will know that B will be going up and this body will be moving in this direction. So will be omega BA because B will go up and I know that this body will be rotating this way. And if this body will be rotating this way, A will be pushed in this way so I can get the omega OA. It will be something like this. So with this, let's see how the velocities look like. So VB will be going up because omega BC is rotating, so VB will be going up. And based also on this omega will be going up. And based on this omega, A will be going this way because I have omega OA is going this way. So here we got the, okay, let's see the instantaneous center of zero velocity. For the instantaneous center of zero velocity, I should make a perpendicular and perpendicular to this line. It's still at the same point, but the omega will be in this way. However, here we have the omega was going this way. So this is the difference. And if we want to get VB with respect to A, given this omega, so VB with respect to A, it will be perpendicular, something like that. And VA with respect to B, it will be perpendicular and will be in this direction. VB with respect to A, perpendicular to this line. So you always look at the omega of the line that you are dealing with and see the direction of the omega and put the V always in the omega direction. It never happens that the body is moving in this way and the V at the end is moving in the other way. That's not logic. Okay, so with this, let's see an application and solve a problem on this concept. I have a problem down here. Yes, this one. Example. Does anybody have any questions on the above concepts or any confusion how you can get the velocities? Let's start this problem. So for this problem, we have a link AB. It's guided by two blocks at A and B, and which moves in a fixed slot. So A is forced to move in the Y direction and B is forced to move in the X direction because of this mechanism. If the velocity of A is 2 meters per second downward, so A is moving down, so I know that B will be going this way, of 2 meters per second, determine the velocity of B. So we are not given the omega in this problem, and let's see what we can do. So what we can do in this problem, if we want to get the velocity at B, so we only have one equation. We cannot think about any other equation. So we have that the VB will be equal to the VA plus VB with respect to A. So VB and VA, so let's see, VB, I don't have the magnitude of VB, but I have the direction of VB in the positive I hat. It never goes in the Y direction where we have G hat. And for VA, I have magnitude and direction. I have 2 in the negative J hat, so it's going down in the negative. And for VBA, as we learned, for relative velocity, it will be the omega of the body BA. So as soon as this body, this point is moving this way and this point is moving this way, so this body is making an omega this way. So this is the omega AB. So the body is sliding like this. So that means that the body is rotating this way. So this way, if I put my right-hand rule with the omega AB, so the K hat is going in the positive direction towards me, so I can remove the vector from above and say this is K hat, and we will cross this with RB with respect to A vector. So let's get RB with respect to A. So this is point A, and this is point B, and if I get this, so this is RB. RB with respect to A is constant in magnitude, but the direction keep it changing. So let's write this equation, VB I hat equal -2 J hat plus omega BA, which I don't know, K hat crossed pi RB. So let's get the vector of RB. So RB is negative this and positive this. So let's see how much in y direction and how much in the x direction. So we have here, this is 2 meter, and yeah, so here's determine the velocity VB at the instant where theta is equal to 45 degree. So if this angle is 45 degree, so, and we have this as my vector. So my vector will be something in the x and something in the y. So this will be 2 cosine 45, and this is 2 sine 45. So it will be -2 because it's going down in the j hat and +2 sine 45 in the I hat. So 2 sine 45 in the I hat and -2 cosine 45 in the j hat. Okay, if you want to do the cross product, I usually draw this so I don't make any mistakes. I have I, J, and K. And as I go from K to I, it will give me J, and from I to J, it will give me K, and from J to K, it will give me I. Okay, so let's have the equation here. VB in the I hat vector will be equal to -2 in the J hat vector plus. So let's multiply omega BA in the K hat multiplied by I hat. If I multiply K by I, it will give me positive J. So it will be 2 sine 45 multiplied by omega BA. So this is the magnitude, and the direction will be J hat plus. So let's multiply K by J, and we have negative sign here. So if I multiply K by J, I go negative this direction. So if I multiply K by J, it will give negative I hat. And we have negative outside, so it will be positive. So it will finally end up with 2 cosine 45 in the I hat direction. So right now we can solve in x direction. So for x direction, which means the I hat, we will have VB. So this is the I hat, and this is I hat. So VB will be equal to 2 cosine 45. And in the J hat, which is the y direction, we have 0, nothing on the left-hand side in the J hat, but we have here -2 plus 2 sine 45. Yep, and this should give us, oh, sorry, I forget the omega, BA. So this should give us omega BA equal to 14.18 radian per second. And this should give us that the VB will be equal to 1.9. Oh, sorry, I think I forget something. So, yep, here we are multiplying omega BA by this term and omega BA by this term. So this should be 2 cosine 4 omega BA in the I hat. It's K multiplied by J in the I hat, so I forgot omega BA here. So this one shouldn't be like this, so it should be 2 cosine 4 omega BA, and I should get omega BA from this 2, which is here, and finally I get VB, which will be equal to cosine 45 multiplied by 14.18, and this should give us 1.96 meter per second. So this is how we solve this problem. We construct the relative velocity equation between B and A, and we got some components in the I and some component in the J hat. You should be able to do cross product and you know the directions, because if you get the directions right, it will affect your final answer. And also be sure that you included the magnitudes. So we multiply the magnitudes, omega BA 2 sine 45, to get the magnitude, and multiply K hat by I hat to get the direction. So this for this problem, let's solve another problem here. So we have this example. So for this example, does anybody have any question on the previous problem? Okay, let's move to the next one, which is a little bit more interesting. So for this one, we have a cylinder that crawls without slipping on the surface of a conveyor belt. So we have this conveyor belt is moving like this, which is moving in 2 feet per second. So we have this point is moving, or all this belt is moving with 2 feet per second. Determine the velocity of the point A, and the cylinder has a clockwise angular velocity omega 15 radian per second at the instant shown. So right now it needs the velocity of A. But to get the velocity of A, we will be using the velocity at B. So we can say that the V at A will be equal to the V at B plus VA with respect to B. Okay, so let's see how can we get this. So the V at B is given, like all this conveyor belt is moving with 2 feet per second. So the velocity here is 2 feet per second as well. And the VAB, it's the omega multiplied by RA with respect to B. So we need to get this RA with respect to B. So VA vector will be equal to VB vector, and we know VB is moving in the X direction, so it will be 2 as a magnitude in the I hat direction, plus VAB is equal to omega AB crossed by RA with respect to B. Omega AB is moving this way, so it's 15 radian in the negative K hat direction, so it will be negative 15 in the K hat direction, cross product by RA with respect to B. So this is how it looks like. This is RA with respect to B, and you should move up and you should come here, and this should be 45, and this is also the radius 0.5. So this will be negative 0.5 in the I hat direction, which is this one, and positive 0.5 in the J hat direction. So you know that you will have to go up in the positive J hat and go this way in the negative I hat. So let's do this product. So we'll have 2I hat plus. Okay, let's multiply here I, J, K. So I'm going from K hat to I hat, and negative multiplied by negative will be positive. So moving from K to I will give the positive J direction. So it will be 7.5 in the J hat direction. Let's multiply the K by J. K multiplied by J, it will be in the opposite direction like this. So it will give you negative I hat. And we have negative already outside. So negative 15 multiplied by positive 5. So it will give a magnitude of negative 0.75. And we have negative I. So it should give us plus 7.5 in the I hat direction. So the VA in the X direction, we will sum all the I hat components. So we'll have 2 plus 7.5. It will give us 9.5. The VA in the Y direction will be only 7.5. So V at A will be equal to 9.5 in the I hat direction plus 7.5 in the j hat direction. If we want to get a magnitude, so it will be plus 7.5 square, and this should be equal 12.1 feet per second. And if you want to get the theta, so it will be tan inverse 7.5 over 9.5, and this should give you 38.29 degrees. And actually that makes sense if we look at A. So, and we have this cylinder is moving this way, so omega will be something like this. We'll make VA moving this way. And it makes a positive 2 plus 7.5 will be 9.5, and you will have a j hat as a 7.5. So that makes sense if we want to get the A. Okay, does anybody have any question on this problem?
Yeah, how did you get RAB again?
Okay, RAB, so let's clean this. Okay, so we will have to determine where is A, and at the circle at this point, and get here. And then we know there's the center of the circle, so this is R, and also this is R. So we know if we want to move this to get at this point, we will have to move R in the positive j hat and another R in the negative I hat. So the magnitude of the RA with respect to B, it will be the root of R squared plus R squared, but we need it as a vector. So we need to know how much in X direction and how much in Y direction. And this is how you can get it. So it's this part plus this part. Or if you want, you will get this angle as a 45 degree, and then you will have the R as a magnitude. Sorry, this is the RA with respect to B, and you can get, here's RA with respect to B, it will be root R squared plus R squared, and you get the magnitude, and you know the angle, and then you get R cosine theta and R sine theta to get the R in X and R in Y direction. Did you get it, or still confused?
No, I get it now. Thanks.
Okay, so like here, and you know this is R, and this is R, and you have this as the RA with respect to B. So you know to get this point, you will have to move this and then like this. So right now you have the X and Y component. You don't have to go all the way to get the magnitude of R and then get this angle and determine the a short route. And also with this, I would like to mention one last thing. If you are driving your car or a bicycle, it's something similar to this, but the thing is that the ground is not moving. So now you have a conveyor belt that is moved. So it means that the ground is moving with respect to this cylinder. But if you are driving your bike, and this is the wheel of your bike, and this is the ground is not moving, so V at B will be equal to 0. And when we say that V at B is equal to 0, that means that VB is an instantaneous center of zero velocity. Because the ground is not moving, so the V at B is not will be equal to 0, and we will be discussing the instantaneous center of zero velocity in details in the next lecture. But just like I would like to mention that this problem is something similar, but here we have the conveyor belt is moving. That means that the ground is moving. But when you are driving your car or driving your bicycle, the ground is settled and is not moving. So the V at B will be equal to 0, and you will have that VA with respect to B will be equal to VA. Yes, that's it, and see you guys tomorrow. Does anybody have any question, like on this? Any other questions? Okay, I think we have a help session today, right, at 1. So if you have any question, just like stop by and come and ask any question related to the midterm or you are preparing for the exam. The quiz will have multiple questions and it will cover the last two lectures and maybe I don't think, but the information that I give you here, it will help you also to solve the quiz, just like try to cover this lecture as well. But if you were able to cover the last two, it should be